So one very basic result in this direction is Dirichlet's approximation theorem. So this theorem says if alpha is a real number, then for every x in the natural numbers, there exists a pair of integers which are co-prime, and where x is between 0 and q is between 0 and capital X, such that alpha can be approximated by a divided by q in such a way that alpha minus a divided by q is less or equal 1 divided by qx. This result is as a consequence an easier to understand result, namely if alpha is an irrational real number, then there exist infinitely many pairs AQ of integers which are co-prime and for which q is greater than 0, such that alpha can be approximated by a divided by q in such a way that alpha minus a divided by q is less than q to the minus 2. In some sense, these are good approximations to alpha. A proof of this theorem is pretty easy. It can be done using the pigeonhole principle, but can also be done explicitly by a continued fraction expansion of alpha. So these a divided by q's are particularly good rational approximations of alpha. There is an equivalent formulation which is as follows. Let alpha be an irrational real, then there exists infinitely many q such that the distance of q alpha to the next integer is less than q to the minus 1. So just to see that, just multiply this inequality, the inequality alpha minus a divided by q less than q to the minus 2 by q, and what you get is q alpha minus a less than q to the minus 1. Yeah, so therefore equivalently you can say that distance of q alpha to the nearest integer is less than q to the minus 1. So this consequence, which I wrote here, is the same as saying that distance of q alpha to the next integer is less than q to the minus 1. Okay, so now the question is, how well can I approximate actually a given irrational number by rational numbers? So I want to stick throughout my talk through that equivalent formulation, which I gave above. So one can always formulate these results about Diophant approximation by rationals, either in form of this inequality, alpha minus a divided by q modulus is less than so and so, or when we multiply by q, we get an inequality of the form the distance of q alpha to the nearest integer is less than so and so. That means this quantity on the right hand side multiplied by q. Okay, so therefore we want to ask the following fundamental question in Diophant approximation. Given some irrational number, yeah, what can be said about, so for which exponents gamma can be proved that the distance of q alpha to the next integer is less than q to the minus gamma? Or more precisely, what can be said about the supremum of all gammas such that distance of q alpha to the nearest integer is less than q to the minus gamma? So how well can we approximate alpha by rational numbers? That's the question. So now Khinchin's, there's a theorem by Khinchin which implies the following. So for almost all irrational alpha, this supremum is equal to 1. However, one can find irrational alphas for which there is much better approximation by rationals than for usual irrational alphas, meaning that the supremum, which I talked about, is larger than 1. And in fact, one can make the supremum as large as one wants. They are so-called Liouville numbers, which are particularly close to rational numbers in some sense. So that means one can make this gamma here arbitrarily large and still gets infinitely many q's. Okay, so one has numbers with particularly good approximation by rational numbers, but on average, yeah, so for almost all irrational alphas, it is just as good as given in Dirichlet's approximation theory. So remember, Dirichlet's approximation theorem says that or implies that for every irrational alpha, there exists infinitely many q, such that distance of q alpha to the next integer is less than q to the minus 1. And so this theorem of Khinchin implies that this minus 1 cannot be improved for almost all irrational alphas. So for almost all alphas, this exponent is optimal, in fact. Okay. Yeah, so to be precise, okay, one more very important theorem, which actually resulted in the Fields Medal, the highest award in mathematics. Roth's theorem, which says that if alpha is an irrational algebraic number, then the supremum is in fact 1. So that means for algebraic numbers, we don't have an extremely good approximation by rational numbers, but just an approximation not better than given by the Dirichlet approximation theorem. Okay, so to be precise, Khinchin's theorem can be put in the following form. So he formulated it more generally. Instead of considering inequalities of the form q alpha, distance to the nearest integer, less than q to some power, he considers less than a function psi of q. So where psi is a non-decreasing function, so psi goes from n to r plus, the positive real numbers is non-increasing, sorry. So then for such a function, a real number alpha is called psi approximable if you have this inequality. Q alpha, the distance of this number to the nearest integer is less than psi of q for infinitely many q element epsilon. So when we have this inequality for infinitely many q, then we say that alpha is psi approximable. And so what he proved is that, if this series q equals 1 up to infinity, psi q diverges, then almost every real number in the sense of the Lebesgue measure is psi approximable. And if the series converges, then almost every real number is not psi approximable. So when you consider psi given by q to the minus gamma, as in the previous slides, then you observe Khinchin's theorem implies if gamma is less or equal 1, then the series, since the series in this case diverges, almost every real number is psi approximable. But if gamma is greater than 1, then since the series diverges, almost every real number alpha is not psi approximable. Okay, so I have written that in this form. So Khinchin's theorem implies if gamma greater 1, then for almost all irrational alpha, this inequality is only finite element solutions. And if gamma is less or equal 1, yeah, then we know in this case, we know anyway from Dirichlet's approximation theorem that for all irrational numbers, this inequality holds. So important is Khinchin's theorem implies that if gamma is greater than 1, then for almost all irrational alpha, this inequality has only finite element solutions. So in other words, there are very few alphas for which we have extremely good approximation by rational numbers, in the sense that q alpha, distance to the next integer, is less than q to the minus gamma. Okay, so there is a conjecture in this direction, namely essentially saying that we can drop this condition of non-increasing. So I wrote this here. Remember, in Khinchin's theorem, I said psi is supposed to be non-increasing. So there's a conjecture which essentially says that this condition can be dropped. That's a so-called Duffin-Sheffer conjecture. Duffin-Sheffer conjecture. Yeah, so here there's no condition on psi to be non-decreasing. The series looks a little bit different, but it says essentially the same as the Khinchin theorem under the weaker condition that psi is any function from n to r plus. So that's an important, or has been an important conjecture in the Diophant approximation. And this has been proved recently by Kokolopoulos and Maynard. So these are very bright stars currently in analytic number theory. Mathematicians which proved a lot of important results recently, and one of them is the Duffin-Sheffer conjecture. Okay, that I just want to mention because this was just recently established. Good. I also mentioned earlier Roth's theorem, which says something about Diophant approximation of algebraic numbers, so numbers which are roots of polynomials with integer coefficients by rational numbers. So the celebrated theorem by Roth from 1955 says that if alpha is an irrational algebraic number, then for every epsilon, this inequality q alpha, distance to the next integer less than q to the minus 1 plus epsilon, is only finite element solutions. So in other words, so this infinitude of yeah, okay, let me just stay at this slide. The infinitude of q's such that q alpha, distance to the next integer less than q to the minus gamma, holds only for gamma less or equal 1. If you make gamma a little bit larger than 1, you get only finite element solutions. So in other words, yeah, when you go back to this original formulation of the Dirichlet approximation theorem, it says the following. So alpha minus a divided by q modulus is less than q to the minus 2 for infinitely many pairs aq, which are co-prime. We can put Roth's theorem also in a form which resembles this original inequality, namely The inequality alpha minus a divided by q less than q to the minus 2 plus epsilon. So a little bit larger than 2 is only finite element solutions. So that means for algebraic alpha, if you make this 2 a little larger, replace it by 2 plus epsilon, then you get only finite element solutions. So this exponent 2 here is optimal. And if you put your inequality in this form below, then you cannot choose the exponent larger than 1. Otherwise, you have only finite element solutions of this inequality. Okay, so these are very important results in Diophant approximation. Let me say something more about Rhodes theorem before I turn to the real question of this talk. So this question of approximation of algebraic numbers by rational numbers has a long history. That started already with Liouville, a famous mathematician from the 19th century. So he proved a weaker result. He proved that if alpha has degree, or let's say we denote the degree of alpha by, so the algebraic degree of alpha by degree function alpha. So then he showed that this inequality above has only finitely many solution with an exponent 1 plus epsilon replaced by degree alpha minus 1 plus epsilon. So for quadratic irrationals or quadratic irrational algebraic numbers, this coincides with Rhodes theorem. But if you have irrational numbers of higher degree, then he gets a worse result. For example, if you have a cubic algebraic number, he gets only an exponent of 2 plus epsilon instead of 1 plus epsilon, for which he can show that there are only finitely many solutions. Okay, but this was the first result in this direction, and then there were intermediate improvements due to Siegel, Dyson, and finally Roth proved the full statement, which is actually sharp, so one cannot get better, of course, in 1955. Good, so now after having given you a flavor of Diophant approximation by stating some celebrated theorems in this field, let me turn to the question of this talk and related research about this question. Okay, so the fundamental question which I formulated was, essentially, for which exponents gamma can we show that this inequality here, q alpha, distance to the next integer less than q to the minus gamma, is only finitely many, is infinitely many solutions. That's the question. Okay, so now we can extend this question, or we can generalize this question. We may ask, what happens if we restrict the set of q's to a subset of the natural numbers, an infinite subset, maybe some arithmetically interesting subset of the natural numbers. So what can be said about this exponent here? What can be said about the supremum of all exponents, gamma, such that this inequality has infinitely many solutions? So now there are a lot of interesting or arithmetically interesting subsets S of the natural numbers. A particularly interesting subset is the set of primes. So equivalently, what can be said about approximation of irrational numbers by rational numbers with prime denominator? That's the question. There are investigations also about other interesting subsets of the integers, for example, square-free numbers. But let's focus in this talk on prime numbers. So for how many prime numbers do we have a particularly good approximation of a given irrational number by a fraction a divided by p, where p is a prime number? Good. So more precisely, the question is the following: that alpha be an irrational real, for which taus can be proved that there exist infinitely many primes p, such that the distance of p alpha to the next integer is less than p to the minus tau plus epsilon for every epsilon greater 0. Okay, so we expect some result similar to Dirichlet's approximation theorem. So that means we expect that we can choose tau here equal to 1, so that this inequality holds for infinitely many primes p. And in fact, so this would follow from a very strong conjecture about primes and arithmetic progressions. However, so one cannot remove the epsilon here. In the Dirichlet approximation theorem, you don't have an epsilon. You have this statement with tau equal to 1 without an epsilon. One cannot remove the epsilon here. This was shown by Harman. So he has shown that there exist irrational number alphas for irrational numbers alpha, for which one cannot do better than this inequality here. So one can show only the infinitude of primes satisfying this inequality, but not better. So this implies that we cannot do without this epsilon here. Okay. But so what is known in this direction is much weaker. In fact, it is only known that we can choose tau equal to 1/3 as an admissible exponent. So we can show for infinitely many primes, one has this inequality distance of p alpha to the next or nearest integer is less or equal p to the minus 1/3 plus epsilon, something much weaker. But this is considered the limit of the current technology which we have in analytic number theory, because in fact, even under the generalized Riemann hypothesis, a very important hypothesis in our field about L functions, one has not a better result than that. So one does not know how to do better than 1/3. Except one assumes very strong hypothesis on the least prime in an arithmetic progression. Okay. So this problem has a long history, is a very well-known problem in analytic number theory, because it has triggered the development of important tools in analytic number theory. So Vinogradov in the 30s of the last century proved that result with the exponent 1/5. So that's weaker than 1/3, what is known now, but the first non-trivial result. So what allowed him to prove that was a deep non-trivial treatment of trigonometrical sums over primes. This is also important, this non-trivial treatment of trigonometrical primes, trigonometrical sums over primes. Is also other consequences, like one can prove unconditionally the Ternary-Goldbach conjecture. So the Ternary-Goldbach conjecture says that every large enough odd number can be written as a sum of 3 primes. So using this non-trivial treatment of trigonometrical sums over primes, he gets a bunch of important consequences. One of these consequences is this result. So this Diophant approximation in the form given above with an exponent tau equals 1/5. Okay, so now the question was, can one improve this 1/5? Much later, Vaughan came with a result which improves 1/5 to 1/4. So this is an important paper because he introduces a very convenient identity, the so-called Vaughan identity, for a function, the von Manuel function, which is closely connected to the indicator function of the set of primes, which allows a nice decomposition of this von Manuel function, and in particular allows to treat such trigonometrical sums over primes in a much easier way than Vinogradov did in the 30s. So this Vaughan identity is very useful whenever you have sums over primes, in particular trigonometrical sums over primes. He also improved some of the Fourier analytic arguments in Vinogradov's work, and was able to achieve this exponent 1/4. So then in subsequent work, people came closer and closer to this exponent 1/3. So in a also important paper, Harman introduced a sieve method, a special sieve method, which since has become an important tool in sieve theory, which allowed him to obtain the exponent 3 divided by 10. Then, so this work has been refined several times, in particular by Harman himself. And finally, new ideas were introduced into the method by Heath, Brown, and Gia, using Klosterman sums. Good, I will not say anything about that, but Klosterman sums are appearing very frequently in my field. And there are deep connections of Klosterman sums with algebraic geometry on the one hand, and on the other hand, two automorphic forms. Okay, so exploiting these connections, finally, Matomeki, in a landmark paper, achieved this exponent 1/3, which is considered the limit of the current technology. Okay. Yeah, so my own work is related to generalizations of this question to number fields. In a very recent paper in 2019, Harman himself considered the same problem in the setting of Gaussian integers, so in the ring Zi instead of Z. So all numbers of the form a plus bi, where a and b are integers, I the imaginary unit. So also in this ring, one can make sense of this question. I will say something about this later in this talk. And in this setting, he obtained a result which is comparable to his 1996 result. So he got an exponent of 7/22 again by carrying over his method from 1996 to this more general setting of the number field Qi. Okay, so then more generally for imaginary quadratic fields, Mark Technow and myself considered this question and got 1/4, exponent 1/4 of Vone. Then in even more recent work, my PhD student, Vaipal Mazumdar, and myself got the same exponent for real quadratic fields, which is in a sense more difficult because there are additional obstacles like the infinite unit group. Yeah, in particular, the infinite unit group causes trouble, and also the problem becomes, instead of one-dimensional, becomes two-dimensional. Okay, so in this year we've achieved the same exponent of Hamann in general for quadratic fields, so for both imaginary quadratic fields and real quadratic fields. Okay, so now of course there's a lot of space to do improvements. We would like to have Matomeki's exponent 1/3 in this connection. And we would also like to extend this work to higher degree number fields. But there are many difficulties to overcome here, so it's not easy. It gets technically quite complicated, this whole stuff. So therefore, I've decided not to talk about the techniques used in the number field case, but rather give a little bit of an idea of the techniques used to treat the base case of Z, so rational integers and rational primes. Okay, so now, yeah, there is still a little bit of time to talk about so the basic ideas which go into the method. Yeah, so I'm talking about this original question. Let me go back to this. Yeah, so the original question, I state it again. Let alpha be an irrational real number for which tau can be proved that there exist infinitely many primes, p, such that the distance of p alpha to the next integer is less or equal p to the minus tau plus epsilon. Okay. So good. So since Hamann's work, all people use Hamann's sieve method as a basis. So the difference to Vone's work is Hamann's sieve method is more, I mean, so it leads to similar kind of sums, but Hamann's sieve method is more flexible. Instead of asymptotic estimates, we get here only lower bounds for certain sums over primes, but we have more flexibility in the method. So basically, that's the advantage of a sieve method of Hamann's sieve over Vone's identity. Okay, and since Hamann came up with his sieve, all of these authors have used his sieve method as a basis, or as some basic ingredient. Okay. All right. So what are the basic ideas going into the method? Yeah, so this is, first of all, we make use actually of Dirichlet's approximation theorem. That means of approximation of alpha by general rational numbers A divided by Q. So then, as I said, we use Harman-Sieve, a sieve method to detect primes. So there are many sieve methods. Harman-Sieve is a particular sieve, which is especially suited for this situation. So Harman-Sieve is a comparing sieve. In this setting, we compare two quantities. So what we are interested in is, so we consider primes in dyadic intervals. Let's consider in dyadic intervals between n and 2n. So then we want to count the number of all primes in such dyadic intervals, such that p alpha, the distance of p alpha to the next integer, is less than delta. So the probability that we have a distance of p alpha to the next integer is less than delta is about 2 delta, if you pick some random prime p. So that means this should be approximately of the same size as 2 delta times the total number of primes in this interval, n to 2n. So we compare these two quantities. So Fi p alpha measures precisely the number of primes p such that p alpha is distance less than delta to the next integer. Okay, so we compare these two quantities. All right. Sorry. So what we shall show, or what we can show, is that the difference between these two quantities is in fact very small. So I say these quantities should have the same size about. We show that the difference between these two quantities is very small. And so the advantage of the second quantity, 2 delta times the number of primes in the interval from n to 2n, is well under control because we know what approximately the number of primes in such an interval is by the so-called prime number theorem. Okay, so the philosophy is to detect primes in two different sets. Okay. Let me show you that how it works in general, the sieving. So in general, in sieve theory, the task is the following: when we have given a set M of integers, a finite set M, then we want to know the cardinality of all integers, little m, in this set, capital M, such that M is not divisible by a small prime, p less or equal some parameter z. So that means from a given set of integers, we sift out all integers which are divisible by primes less or equal some parameter z. So then the central task of sieve theory is to get lower and upper bounds for this cardinality here. Okay. So one can detect actually primes in set of integers. So if you choose M to be a subset of a dyadic interval, let's say from n½ to n, and you say that this parameter z here is equal to n½ then what you see for are exactly primes. So then this cardinality of sifted elements, after you remove all multiples of primes less or equal z, is in this case precisely the number of primes in the set. Okay, so Harman-Sieve is a special sieve which compares these quantities for two sets A and B. So the idea is to take two sets A and B and compare SAZ with SBZ where we assume that B is large enough so that SPZ is well understood. Yeah, of course, if you have a thin set, a small subset of the integers, then it's difficult to detect primes. But if you have a large subset, I mean, for example, a whole interval, then it's easy to detect primes because we have, for example, the prime number theorem, which gives us information about that. Okay, so how does it look like in this problem? So for our set B, we take just the natural numbers in the interval from n½ to n. And for A, we take a set of all integers such that the distance of n alpha to the next integer is less or equal to some given small delta. Okay, so now the task is precisely to detect primes in these sets and compare the quantities of these primes. So we take in the Sieve setup, we take z equal to n½ and then SPZ is nothing else than the number of primes in this interval, n½ to n. And SAZ is the number of primes in this interval which satisfy this extra condition, the Diophant approximation condition. Okay, so we have an expected relation between these two quantities. So now the task is to prove that. And to this end, one has this Hammond sieve. So now it becomes very technical and I will cut the details. I just tell you what Hammond sieve does is to boil down the problem to so-called type 1 and type 2 bilinear sums. So what one does is one considers bilinear sums of this form. So let's consider first these type 2 sums, the second type of sums. So one lets m run in some interval and n run in some interval and assumes that mn is element of A. Then one considers the sum of all am, bn, where m and n satisfy this condition. And one compares them with similar sums, where one has instead of the condition mn element A, the condition mn element B. If the sums on the left-hand side are about of the size of the sums on the right-hand side, then one is in a good situation. One can actually prove this relation, which I mentioned before. So I wrote on the last slide, we expect that SAZ is approximately of the size of 2 delta SPZ. So Hammond sieve gives us a relation or gives us a way to relate that problem to certain bilinear sums. So where on the left-hand side, the sums involve the set A, and on the right-hand side, the sums involve the set B. And if these sums are comparable in size, where we have a certain scaling factor on the right-hand side, then we can deduce that the sieve quantities are comparable to each other. That is precisely what we want. So now I cut out all the details. So we use now, in fact, Fourier analysis to detect the Diophant condition here. Fourier analysis comes also into play. Then things boil down essentially to exponential sums, linear exponential sums. So in the end, one is just led to exponential sums of the form sum of n in some interval e of nx. E of nx means e to the power 2 pi I nx. So that's a trigonometrical sum. Of course, we can replace that by cosine 2 pi nx plus I sine nx. Okay. Good. So what comes into play is Harman-Sief method and Fourier analysis. And in the end, one is led to some counting problem. And here in this counting problem, one needs this Dirichlet approximation theorem. So there are basically three tools: a Sief method due to Harman, which is particularly suitable for this in this context. Then one needs Fourier analytic methods, and one needs Dirichlet's approximation theorem. Okay. Good. So in my slides, I put some asymptotic form of Harman-Sief. So this gives only this bone exponent 1/4. One can make this Sief method a lower bound Sief. In this case, one can improve the exponent because one has more flexibility for the choice of the parameters in this Sief method. So that is something which I want to mention here. So I consider just the simplest setup of the Sief here in my slides. One can do better than that. Okay, I don't bother you with the technical details. Just so now, this recent research is about the number field setting of this question. As I said, Harman and my collaborators and me, we have done that for quadratic fields. Let me just give you an idea of that by looking at the simplest quadratic field, the field of Qi, where we adjoin I to the rational numbers. Okay, here I have mentioned our results again. Let me just show you how this works for Qi. So in this setting, we take, instead of alpha irrational real number, we take an irrational number in the sense of alpha is contained in C, but not in Qi. So instead of alpha element R without Q, we consider alpha element C without Qi. Okay, so then there's also a notion of the distance to the next integer, namely what we need to consider here is the next Gaussian integer. So the ring of integers in Qi is the ring Zi, Z adjoint I. These are all complex numbers of the form a plus bi, where a and b are in Z. So they form a lattice in the complex plane. And now we can again, of course, consider any complex number and the nearest Gaussian integer. So the nearest element of this lattice. Good. So then what we can ask, so we can define the distance function by taking the usual Euclidean norm, or we can also take the supremum norm. Doesn't matter. So now we ask, when we take prime elements in this ring, so Gaussian primes, in this ring Zi, what can be said about distance of P alpha, so prime elements P, what can be said about distance of P alpha to the next Gaussian integer? And so Harman in 2019 showed that the distance of P alpha to the next Gaussian integer is less than modulus of P to the power minus 7/22 plus epsilon for infinitely many Gaussian primes P. So that means it's just a generalization of his classical result, so of his result for primes and the integers, two Gaussian primes. So he carries over his method, but it's not completely straightforward generalization. There are a lot of technical challenges or difficulties which he has to overcome to make this work in this setting of Gaussian integers. Okay, and we have driven this further by looking at imaginary quadratic fields first in general, and then real quadratic fields, which are in a sense different because then the problem is two-dimensional. But in all these settings, the tools which I mentioned before are available. So there is a generalization of the Dirichlet approximation theorem to number fields. One can make a Harman-Sief work for number fields. So then one needs to consider an ideal version of this Harman-Sief. And of course, one has all these Fourier analytic methods also in a multidimensional setup. Good. So one thing which I'm not able to touch here is recently, Sudhir Pujahari, a collaborator of mine, and myself, we have considered a p-adic version of the problem. So one can even consider that problem in the context of p-adic numbers. I have no time to go into that. Interestingly, so this problem relates to primes in arithmetic progression, more precisely to the least prime in an arithmetic progression. I already mentioned, so there's a connection of this Diophantine problem, which I consider here class or in an arithmetic progression. And if you consider the p-adic version of this problem, then you get much more directly a connection to that problem. How large is the least prime in the residual class? Okay, but I cannot say anything about that because my time has run out. Okay, so there's a lot to do in this direction. So we are just at the beginning of these number field generalizations of the problem. Lot of work for future future generations of number theorists. Okay, thank you very much for your kind attention. Then I close my talk with that.
Thank you, Dr. Stephen, for your nice talk on approximation theory. Thanks for joining us. Thank you, Dr. Stephen. Can you hear me?
Yeah.
Yeah, okay, thank you. Thanks again. And I'm sure that those working on approximation theory or interest in the field of approximation theory and its application will surely be benefited by this lecture. And we know that approximation theory is applied in numerical analysis and many branches. Those who are working may use approximation theory. So thanks, Dr. Stephen, again.
Yeah, thank you very much for the invitation. I'm very happy to be here. It's an honor to speak at this conference.
Welcome. And I request someone who want to ask anything or have a confusion in this talk may ask the question, may raise hand. No one? So thanks, Dr. Stephen.
Okay, thank you again. Yeah.
next lecture, next talk will be by Professor S.S. Mishra, who is the faculty member of this Department of Mathematics and Statistics, Dr. Rammanohar Avadh University, Faizabad, Ayodhya. He joined this university, Dr. Mishra joined this university in 1993. Period to this, he was a statistical officer in the UP government. In 93, he joined this university and worked on various posts. He is the head of the department nowadays. And he is also the director of the Institute of Physical Sciences and Yogic Sciences of this university. He has also done DSc, Doctorate of Science, from this university, PhD from this university, and also MSc from this university. He has a number of research papers to his credit, and so many students have passed PhD, have taken PhD degree under his supervision. He has also supervised 2 research projects. One is going on of the DST, and his topic of interest is the queuing theory, operational research and its application. Today, he is talking on the topic queuing model with ANN and its applications in SCS. So, with this brief introduction of Professor S.S. Mishra, now I request Professor S.S. Mishra to please start his lecture on queuing model and its application. Please, Dr. Mishra.
Okay, thank you very much, sir, for your nice words about me. Today, I am going to present a lecture which is focused on the queuing model with ANN and its application in the area of the healthcare system. So this title has 3 important aspects. One is the queuing model itself, and second one is artificial neural network, because this queuing model has been made artificially intelligent. In other words, we can say like this. And when queuing model becomes the artificially intelligent, then how we can use this artificially intelligent model to the healthcare system. Application in the healthcare system means the main purpose is how to improve the healthcare system. So we would like to discuss one by one under the main highlights. And I will try that you should not get bored, because this is the 3rd day. So I would like to be on the light mode. My voice is going clearly, Sankarji?
Yes, sir. Yes, sir.
Okay. Okay. So this is the abstract. Now I will explain, then it will come to the proper understanding. Let us come to basics. Introduction. Main highlights of the introduction, then we will come to the implementation analysis of the model. And if we have no time, then I will stop and I will show the application, that how we have analyzed the data with the application of the queuing approach. I would like to just brief about the operational research in one line, that what is the operational research, because my broader area is the operational research. Actually, operational research was born out of the Second World War, and that was the case of the crisis of the resources. So when resources were very limited and the two big powers were, 2 parties were having a war for winning the war with the having interest class, you can say. Both were trying to defeat each one, but both had the limited resources. So it was the responsibility of the engineers, the scientists, the professor, the intellectuals of that society from both of the side. One side was supporting the crisis of the war, it is very difficult for any country to have the resources in proportion to the requirement. So now this queuing theory is part of, after the Second World War, the application of the operational research is spread into several enormous areas, and today nobody can identify any area, any discipline where the operational research cannot be applied. So operational research itself is nothing else but the proper and judicious application of the techniques applied under this branch of science. And this is a common and cross across the board or interfacing area of various disciplines. For example, the mathematics, statistics, engineering, commerce, management, so forth, so on. So it has number of techniques and methods. Now, one technique, one chapter, or one lesson is the queuing theory. So sorry, there was some interruption. So queuing theory, what is the queuing theory? This is very interesting. And it has got very much pervasive nowadays. Anybody cannot tell us each other that I have seen without queue. Queue may be virtual, queue may be actual, this may be on the papers, this may be on the office counter, so forth, so on. So we have number of situations where we face the queuing problems. Now the question arises that why the queue arises. Unless we understand the root cause of the formation of the queue, we cannot handle the solutions and we cannot apply the knowledge of this queuing theory. And therefore, this is the part of the mathematics or the part of the experts of the mathematics that how to handle the concept of the queuing theory. So there may be many regions, many areas where we have the solutions, but once we are as a mathematicians or statisticians, then it is the responsibility to solve the problem from that point of view. So from the mathematical point of view, the queuing theory has been defined as the mathematical study of the waiting line. This is the one single line definition of the queuing theory. This is a theory which is concerned with the mathematical study of the waiting line, meaning whereby we have to only analyze the waiting or queue on the basis of the mathematics and its techniques. Therefore, the queuing theory has become the part of the mathematics from the mathematical point of view. Okay, then further question arises, why we study the queuing theory, waiting line, why we study the waiting line? Because we want to improve the service providing system. Wherever we see the formation of the queue, definitely that is the service providing system. System means it has the theoretical framework, conceptual framework, as well as it has the operational framework. When we talk about the system, it means that includes the office, that includes the software, that includes the procedure set and set of rules, etc. So any system which is providing the service, definitely it has the problem of the formation of the queue. So purpose of studying the queue or waiting line is simply to reduce the waiting line to improve the service quality by less consuming service time. Means if queue is very high on any counter or on any platform, maybe virtual or maybe actual, is not good. Meaning thereby, after studying this as a consultant, mathematical consultant, we can advise the service provider system that your service may be improved by reducing the service time. waiting cost of the customers may be reduced by suggesting particular, device or particular system or particular model. So main purpose of applying the queuing theory to the service providing system is to improve the quality of the service and to optimize the capacity of the system. Means suppose you have the number of servers, number of working persons engaged in the system, some are working, some are not working. If some are working, some are not working, meaning thereby the persons or machines which are not working, definitely they are not doing the justice for the service delivery system. And therefore, the purpose of applying the queuing theory to any service providing system, though here we have taken only one example of the application, that is the healthcare system as a burning issue nowadays for the society. What is the queuing system? I have already explained that queuing system is the conceptual as well as the operational framework of the complete structure of the queuing theory, meaning thereby basic structure includes here. If we talk about customers in the queue, means if we talk about the healthcare system, then they are waiting to enter to get the service. Here is the waiting, here is a queue. Then after having the queue and one by one or parallelly, they can get the service. Parallelly, they can get the service up to this place, and then thereafter, the patient out of the service here, last one. So this is the very simple framework of the queue. In the beginning, they stand in the queue, they enter in the waiting room, they wait for some time, and thereafter they get the service, and out of getting the service, they go back, and then thereafter they provide the feedback to the system. So after having that feedback, system can improve if system wants to improve it. And then that is the role of the mathematical experts or mathematics people to just suggest some improvement over the service providing system. Okay. What is the queuing model? People may say that queuing theory, queuing system, queuing models. So what is the difference between all these terms? Because we frequently and very widely use it. Sometimes we say queuing system, sometimes we say the queuing model, sometimes we say the queuing theory. So what is the basic difference between all these terms? Queuing model is, we have to understand and decipher at this very level, the queuing model is the last operational unit that is based on the mathematical model that will give us the required results or solutions. Queuing system, the complete conceptual framework as well as the operational framework, means when we talk about the queuing system, it means that includes the queuing model. So now I would like to discuss some basic ideas, reason of formations of the queue, why the queue is formed. I have seen this very popular graph. One Mr. Professor Rakesh Kumar from the Namibia, he also used this very graph because he also belongs to the same area of the research in which we are working. But another, the game theory expert from the NIT Nagaland, he was not using this graph for the purpose of the queuing theory, but he also used the similar graph for the horizontal and vertical cooperation in the game theory. So what is why this is so much important? I'm not going to discuss from that point of view what they discussed it, but graph is the same. But I will discuss it from the different angle. What is why the regions of the formation of the queue? Formation of queue is made because we need to fulfill the requirements or demands at once or simultaneously. Suppose 15 persons come and join some service providing counter, and they all say at a time that we want the fulfillment of the service. Is it not possible for any counter which is having the single service provider? Either 15 persons are asking about the service, then 15 servers may be engaged to immediately dispose the, the response of the customers. But 15 persons as a service provider, as a service channel, is it possible practically, theoretically, cost-wise? It is not possible, because every server engages and incurs the huge cost. So it is the whole responsibility and sole responsibility of the system that we need to expend the limited cost for sustaining the system service providing system, and therefore cost is always limited. So we cannot increase the number of servers or number of channels as per the requirement of the customers, and therefore the queue has to be formed everywhere. This is the reason everywhere we see the queue. Then what is the discussion when this is a theoretical concept that this is the cause of formation of the queue? Then what is the role of this graph? I would like to take your attention over this graph, because it has two types of cost. You see, this is cost operating the service facility. This is the service cost. This one is the service cost graph, and this one, another one, is the waiting cost graph. You see, nature of both of the graph. Somewhere you find this is the straight. This is the straight line. You may be curious about this. Somewhere this is the straight line. Somewhere I have not used the straight line. So this actually what happens, the service cost and the level of service. Suppose we engage one server, then cost will be something different. We engage the two servers, then cost will be different. That is from lower to higher. Three service providers, then cost will be much higher. But this increase of the cost is very, very corresponding and proportional. So it is just like a perfect positive correlation, and therefore we find the straight line. Exactly, this is not exact line, exact straight line, but it is similar to a straight line because of the nature of the level of the service and the cost incurred on increasing the service, and therefore sometimes we find it this straight line. Okay, this is, I mean, this one, and you see both are opposite in nature. Both cost have opposition in nature. They are just contradictory in the nature. And here it is very important. Maybe any game theory problem, maybe any inventory management problem, maybe any queuing problem, any kind of this problem where we are going to optimize total cost of the system, because you say that waiting should be minimum. If waiting should be minimum, then what is the responsibility of the system? That the service level must be very high. And if you increase the service level, the immediately cost is incurred. So we cannot increase it. So waiting, customer wants to reduce the waiting, but service server wants to reduce the, waiting cost, or increase the waiting cost. As a server, if you think you want to increase the waiting cost, because if you are single, then you do not incur much of the cost from the system. So nature of intention of both of the cost are just quite opposite. But system has to run, therefore neither side we will take the favor, neither we will take the favor for the waiting means for the customer, nor we will take the favor of the service provider. So we are going to compromise both of the cost, and therefore we talk about the total cost. You look here, this is the total cost, and therefore the point of intersection is compulsory, is inevitable, is compromised. That at this point of the time, this is the service level for the service provider, and this is the cost for, along with this is the cost of the this cost is common for both of it. I mean, both should not quarrel in their own interest. So this is the technical reason, as a technical reason why the queue is formed, why the problem of the inventory is formed, why the problem of the game theory clash of the interest is formed, because at least two casts are opposite in nature. If there is no caste, two casts at least opposite in nature, then problem of the queue would not form, inventory would not form, even problem would not exist. So this is the one justification for the beginners who are going to study the queuing line, this queuing theory, making their career in the field of research. This very technical knowledge was very important. Elements of the queue. Arrival process is here. The persons or customers or the patients come, and then arrival process is very important. Then there is a inter-arrival times, there is a number of customers. So there are two forms. One, either we can talk about the number of customers, or we can talk about the inter-arrival times. So times become the continuous random variable, and the arrival becomes the discrete random variable. Why this is random variable? Because this is not only the random variable, rather it is completely random variable. Completely random phenomenon is this. Why this? Because the arrival of the patient, for example, I take the only example of the healthcare system, the arrival of the patient at doctor's clinic or at the hospital is the quite random, completely random phenomenon. You cannot say, you cannot predict, you cannot assess that this particular patient will come at the doctor's clinic at particular time, particular day, or something else. Because the occurrence of the disease is quite completely the random phenomena. Therefore, arrival of the patients or the customer at service center as a doctor's is completely random phenomena. Therefore, this arrival process becomes the completely random. And if it is a completely random, the inter-arrival times immediately follow the exponential distribution, or the number of customers or the number of patients follow the Poisson distribution. If we talk about in terms of the discrete random variable, then Poisson will exist here. And if you talk about the continuous random variable, then the exponential distribution will exist here. So arrival process is very important. We have the assumption on the basis of the property of the exponential distribution. This is expressed by the exponential distribution in case of the Markovian queue. So this is also a justification of the application of distribution function, a probability distribution function in the form of the exponential distribution, because the exponential distribution has the forgetfulness property or the memoryless property. Now it is the service departure. After having entered into service provider system, what will happen? They will wait for the service. And the service means after taking the service, you will find the inter service times, or the clearly or simply speaking a service time. That service times also follows the exponential distribution, because that time is also completely random. So this will also follow the exponential distribution if Markovian queue is considered. So arrival process is very important phenomena. Its expression, its representation by the probability theory is also very important phenomena. Whenever the moment we express it by the probability theory, the mathematics, the formation, the creation of the mathematics starts, and the role of the mathematicians will start in handling the probability theory. Okay, service is okay. Now, discipline. What are the important disciplines of the queuing theory? So, disciplines are popular disciplines is the FIFO, the first in and first out, first come and first serve. This is the most common discipline which we use, rules which we use for everywhere, but somewhere we will also find the LIFO, last in and first out. Last in and first out is what? This is the stored item somewhere, loading, uploading. the item is inventory is loaded first, but when it is unloaded, then it is going to be last. So the which has been loaded last, it will come first. So this discipline is also, but this is not, the popular one, the frequent one. The another one is the zero service in random orders. We provide the service sometimes randomly as per the requirement of the service, as per the on the basis of the some priority, random service can be also possible. So that is the zero service in random order. And another discipline is the priority discipline. And we most of the time see that I am standing in the queue and some another person comes and he takes or she takes as a customer the service first, and then I get the service. If I make the objection, the service provider says that he is my VIP customer, or something, any justification he can mean service provider can give. So we have to we have to compromise on that situation. So that is the priority service. When we study in aggregate, in totality, this queuing model, then we need to consider the discipline also. We have to mention it. Okay, what is the behavior yesterday? If you look at not yesterday, day before yesterday, the first day, the behavior of the queuing system was given by the Professor Rakesh Kumar very nicely. So there is a three types of the behavior of the customers. Behavior of the customers is the behavior of the system, you can say. So sometimes literature also mention the behavior of the customers, behavior of the queuing system. So both are same. There is no a point of distinguishment, a very serious point of distinguishment. So what is behavior? One is the barking, one is reneging, and another is jockeying. Barking means in the very beginning the customer does not join the queue because he or she sees the queue is very long, then he does not consider to join the queue, and immediately he come back after seeing the long size of the queue. This tendency or this behavior of the queue, this psychology is known as barking. This is not balking, this is barking. Most of the students, even the faculty members, he is the very renowned professor, but still yesterday he was speaking like balking or something else. So we should keep in mind all these minor points. Slowly when we get the higher positions, people start looking at our behavior or something else. This is barking. This is not reneging. This is reneging. Reneging is what we have joined the queue. We have no chance to get the service after a long time. So we wait it, still wait it, but after a time our patience is lost. For the barking customer, patient is lost in the very beginning, but for the reneging customer, the patient is also lost after joining the queue. So this tendency, this behavior of the customer is also known as reneging behavior of the customer. And third one is very interesting, that the jockeying property or jockeying tendency of the system. What is jockeying tendency of the system? In this system, we find that we have joined the queue. We have seen different queue, another queue that is lesser or of having the lesser size or shorter queue. Then we immediately change the queue and join the another queue. We stand for some time and we find that no, what queue? The third one is looking to be very short queue, and if I join that queue, then probably I must get the service in time or very quickly. So the customers keep on jockeying, keeps on this moving from one to another. This tendency of the behavior is this is known as a jockeying. And last time he also is said that barking and reverse barking or anti-barking. Anti-barking means you are just, when I teach our students, they are also connected at this moment of the time. I say that you don't, for remembering the differentiation or distinguishment between the barking and reneging, because whenever we evaluate the answer sheet, sometimes they write the definition of the barking under the reneging and concept of the reneging under barking. Then I say barking means bhagging in the very beginning. You remember this in the bhagging in the very beginning. So perhaps we can make the distinguishment. Okay, anyway, applications. We talk about the applications of the queuing models. Still, we are just covering the basics of the queuing model, and therefore it is important for students, research scholar, and the new faculty members who are going to join this area. This is also a responsibility of mine, that to attract the students in this area for the research and anything. So applications, no any area is left for the application of queuing theory. No any area is left. But prominently, the area in which we can apply the queuing theory is the banking, the agriculture, the commerce, the industry, the healthcare system. So here we have nowadays we have been concentrating on the healthcare system for last last 2 years, because of the some changes in the society. Health issues are the prominent issues nowadays. Okay, now we come to the another aspect of this important topic. I initially brought to the mind of our participants, respected participants, that there are three aspects on which we are going to discuss this very topic. The first one is the queuing theory. The second one is this AI and ML. Healthcare I will come to later, where we are going to apply the knowledge of this. And the moment my time is over, the respected chairman, sir, may indicate I'll stop within 1 or 2 minutes. It will not take much time in stopping my lecture. So when we talk about the AI and ML, nowadays everybody is talking AI and ML. If you are computer, if you are engineering person, this is okay. People say that you are talking in the segregation because you are expert in AI or the ML. AI is what? Artificial intelligence. And what is the ML? The machine learning. Everywhere we people talk about the machine learning. But basically, if ask me whether this, how we can have the depth of this knowledge of the artificial intelligence or the ML, if you have interest in the mathematics, then your footing will be more sound as compared to engineering or other areas, computer scientists, because they do not understand the philosophy, the internal mechanism, how the technique works. They operate it, they get the solution, they recommended their papers, it is published also in very good journals, but they do not understand the philosophy, how the AI works, how the ML works. So let us cover the AI and ML. AI first, intelligence. We talk about the intelligence. Artificial intelligence comes after the intelligence. Intelligence is what? This is the real intelligence. Intelligence means real intelligence or emotional intelligence or the natural intelligence. Who has made this intelligence? If you ask these very basic questions, who has made this natural intelligence in our body, in our mind? As a component, the nervous system, here is the intelligence in the nervous system, but who created this? The nature has created. The biology, natural biology had created the intelligence. And because of that intelligence, we are the excellent species on this universe, on this earth. So that intelligence is the natural intelligence. So is it possible to compare the artificial intelligence with the natural intelligence? That is a big question before the researchers, scientists, professionals, whether the day will come when the artificial intelligence will be equivalent to natural intelligence. And if that becomes the natural intelligence, then what will happen? A robot will behave like SS Mishra. Robot will behave like any particular person, particular personality, and the robot will take over the whole society. The machine will take over the whole society. Then what would be the ethics? What will be the law and order? This or that? So that would be the, I mean, consequences of the developing the machine learning and artificial intelligence. But I would like to say here, this is the human excellence. And if you remember, we worship the god and goddess for this intelligence. Ya Devi, Durga Saptasati, Ya Devi Sarvabhutes, Buddha Rupen Sanstita, Namastasai, 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 Namo Namah. For this intelligence, we worship the god and goddess and nature to have this worship. Nowadays, what people are doing, nowadays people are worshipping the scientists, engineer, mathematicians to provide the artificial intelligence. So instead of praying the God, we can appreciate the person, but we cannot worship the man. The day we start worshiping the man, this society will be on the junk of the, I mean, deterioration. Because the mind would be inflated ego, I mean, arrogance. Arrogance of the mind would become very, very high, and that is the not good thing for this society. Now we also talk about the, I mean, Gyan, Buddhi, intelligence in Srimad Bhagavad Gita. Nahi Gyanen Sadrisam Pavitra Me Vidyate Tat Swam Yoga Sansiddha Kale Natman Bindati. That was the intelligence and knowledge referred in Srimad Bhagavad Gita. We have seen in this Devi Sati. And then what happens this? When we pray the god and goddess, they are super energy and energy like that. They are not the artificial or like this, but we have started. Then what is the artificial intelligence? Biology inspired, the nature inspired, the god inspired, the human inspired, you can say. Real human inspired is known as the intelligence. Then what is intelligence? Intelligence is the power and ability to understand and learn to take the decision. So this is the natural ability inbuilt and embedded with the human being. Then what will happen with the artificial intelligence? What is the artificial intelligence? I have just explained the intelligence. Now, what is the artificial intelligence? Artificial intelligence is the machine-made intelligence. This is the machine-made intelligence. And therefore, this machine-made intelligence means robot will be artificially intelligent. The computer will be artificially intelligent. The service, the receptionist will be working as a robot, and it is working most of the countries. And even I had seen last 2 years that Nepal had employed the receptionist as a robot. So machine is going to take the decision, but I would like to just human, we induce the machine made intelligence. Then is it parallel to the human intelligence? It is very difficult to say. It is not going to be introduced as a real intelligence. So I would like to I wanted to just to change your taste. I'm not able to display the song. I wanted to display a song of, I'm not able to display here. It is not on the screen. I wanted to show you a song of the Kala Kanun, Andha Kanun, film Andha Kanun. हंसते हंसते रोना सीखें, रोते रोते हंसना, जितनी चाबी भरी राम ने उतना चले खिलौना. This is the artificially intelligence. Whatever programming capability we are going to introduce into machine, that much machine will work, not more than this. This is man-made intelligence, machine-made intelligence. This is not the natural intelligence. Then how we can talk about this one? We have studied this nervous system. Human brain has been copied by the mathematicians, by the neuroscientists, by the theologists, by the philosophers, by the computational mathematicians. It is a complete package of the domain of the experts. They sit together and discuss the problem. Then we talk about the artificial intelligence on the basis of the human brain. So how many cells, brain cells, are popularly known as neurons? How many neurons are in the brain? How we can copy the mathematical modeling of the brain? How many neurons are there? There are 86 billion neurons in the mind, in the brain, in the nervous system. 86 billion neurons. And then 86, how much? Billion, 1 billion, how much? Can you imagine? This is very hard. This is very large and very large quantity. This is 100 crores. 1 billion means 100 crores. इकाई, दहाई, सैकड़ा, हजार, 10,000, लाख, 10 लाख, करोड़, 10 करोड़, अरब, 10 अरब, खरब, 10 खरब. Then Neel, 10 Neel. Then the Padam, Mahapadam. And then it goes up to Kharab, Neel, and just like a Padam graded quantity. 86 billion. And if you see how many connections are there in the brain, how many connections are in the brain? How many connections are there? Connections are 10 to the power 15 connections are there in the mind. 10 to the power 15 connections are, means neurons are connected with these connections, interconnections. Neurons means just behave like node, and this is the connection. This is a neuron. Suppose this is a neuron, and this is another neuron. This is a connection between two. So such connections are 10 to the power 15, means at least one padam connections are there. Therefore, artificial intelligence technique is also known as a connectionist technique, connectionist approach, because it is based on the connection. So we have copied these neurons. We assume these natural neurons as a artificial neurons as a node, and these connections as a connections are in biology called synapse. Synapse means connection. I will show you just one graph. This you look here, the brain and the how the synapse function here. Look here. These are the synapse. These are the synapse. Here, this is a synapse. This is a synapse. This is a synapse. This is a synapse. Somewhere may be written synapse here. Yeah, this is synapses. Synapses. Terminals. They are going to connect from another neuron here. So these are synapse, and this synapse transfer the chemical and electrical signals. That is known as a axon somewhere here. Yeah, this is axon. This is the carrier of the signals. What kind of signals are there? Chemical and the electrical signals are just transferred from one neuron to another neuron. I think this is enough for the biology. So this will be just copied and mimicked. Neurons are mimicked as node. Interconnections are known as a nodes and interconnection, just in the means graph theory. And then we have copied the brain of the human being to work it. There are three types of learning. One is the supervised learning, another is unsupervised learning. Supervised learning is what? That is the experience is needed, the past trend is needed, the present experience is needed, then we can take the decision. Working under the supervisor. Working under the supervisor means teacher. Here, teacher is not completely hardware. Last experience is your teacher here. So that is a supervised. That is a supervised learning. Nowadays, and this artificial neural network, this technique is also, this the supervised. Artificial neural network is supervised as well as unsupervised, non-supervised both. Here one term I have left. You can think that perhaps I could not cover it. Simple. So it is a machine learning. Machine learning is what you may be thinking was machine learning. Machine learning is the part of artificial intelligence. It is a branch of the artificial. This is part of the artificial intelligence. Now, artificial intelligence has been graded top 10 technologies in the world by the MIT, Massachusetts Institute of Technology, US. And therefore, machine learning is what? Machine learning is a program. Machine learning is a method of data analytics. So it is a software, it may be the program, it may be the method in data analysis or the data analytics. So it is a machine. Then you will ask, can you give the example of the ML? Yes, regression analysis, the ML, supervisory ML. Supervisory means it takes the data, its experience, its pattern, learn to pattern. You want to learn the pattern. If we have learned any pattern, then we can take the decision for the future pattern. So regression analysis correlation is the ML, the multiple regression is the ML, logistic regression is the ML, everything is ML. So it is a method, not any human being or something. Method is treated as a machine because hardware is not taking dominance over this. So machine means any method. Okay, we have completed it. We have supervised learning. This is the example of the supervised learning. Target is here, input is here. We go to the target. We come back again. This is the bias, plus minus bias. When we take the decision, the bias is inevitable. You cannot ignore the bias in the human process. This is the supervised algorithm. Now this graph is disturbed some little bit. Someday. So unsupervised training is also kind of training under which we develop the artificial neural networks. Unsupervised means there is no, past experience, or your teacher is not given here. You are not given a teacher. You are not given the experience. So you have to take the decision, develop the decision yourself. And what are the examples? The genetic algorithm is the unsupervised learning. And clustering method. Clustering K means also the case of the training set. If we have data, then how we can define how much data we consider for the training set, how much data for the test set. There is a thumb rule regarding this. Little bit deviation, that if suppose we have the 100 data, then we take the 80% data for the training. On this basis, the further prediction will be taken into cognizance. 80 and 80 is to 20. This is the 20 part test. The training of the data, we train the mind, we train the artificial intelligence according to this data. 80% data is trained to take the decision, further decision. And this training is okay or not, testing will be made to 20% data. Then further a question arises, what is the training and validation data? So out of the trained data, 80% would be, sometimes you will also find the 70-30 or 75 and 25, but majority of the literature, majority of the professionals say like 80-20. The trained data, and this is the for the validation data. Okay, I have what is the healthcare system? Healthcare system, there is a health provider system where treatment is given by the doctors. So there may be the doctors, there may be some institution, there may be some infrastructure and resources, the paramedical. So it refers to the institutions, the manpower and the infrastructures, and they may provide the low cost treatment. They can provide the medium high cost treatment. And then it refers to the healthcare provider, and the hospital functions are interrelated. Whether the hospitals are having a long queue, whether they are going to have the shorter queue, whether the service time is much high or service time is low, whether the doctor's efficiency is completely utilized, that is the load factor. Is it the capacity is appropriate or not, or capacity is available, then it is not being utilized, optimally utilized. These are the burning areas of the healthcare system, and we have seen that healthcare system is not working properly. Then how we have taken this challenge to study through the queuing model. Our queuing model has become the artificially intelligent. So now artificially intelligent queuing model is going to enter into the area of the healthcare system. Okay, if we compare, then what happens? Doctors are a server, customers are what? Patients are customer, waiting is there, limited waiting is there, service time is there, random occurrence of the arrival of the patients is there, patient's flow has to be managed by applying the queuing theory. So what has to be managed? The waiting time has to be reduced, service time has to be reduced, the efficiency of the doctors has to be increased. Then how we will be able to solve it? We are going to evaluate this healthcare system by applying the queuing models. What they will do, they will evaluate and they will find the performance major systems of the mathematics, and that will be evaluated and will be applied to find the performance measure. Then suggestion will be made, recommendations will be made on the basis of the, okay, this is all about the theoretical concept AI. Most these are the assumptions. Giving
Sir, please finish in 5 minutes.
Okay, sir. Okay. giving model. No. I am also looking at the time. Okay. I am going to MMQ model. These are types of the models: single server, multi-server models. These are the reality of the life. This is the artificial intelligence. We have done it. You look here, the artificial intelligence. This is the mathematics now. This is the input here, this is the input here, this is the input here, this is the summation junction, that is also known as a activation function. Bias is here. Thereafter we get through the activation function, we get the output. Here is also some threshold value so that we can implement this this model. Synaptic weights are there. You think sometimes that how we take the decision in the awkward circumstances, different circumstances. So these are, we try to give here weights are automatically adjusted according to the implementation of this. This is run by the software. So we are running this thing by the software, very simple software and easily available. Architecture of the, there are several layers of the, this is the hidden layer, this is the hidden layer of the neural network, this is the response, this is the input. These layers may increase as per the applying the parameters. We can increase the number of layers by the software. Doing model analysis, we have seen it. This is the data we have taken according to survey. By the survey we have got the data. What is problem in the healthcare? Which hospital wants to go? Which doctor wants to go? The choice of the doctor, the identification and choice of the doctors. How we can define our choice? We should go or we should not go. So these are the variables factor. What is capacity of the system? How many doctors are working here? What is the facility? This is the per unit treatment cost is here. Waiting line, number of persons, how many waiting line. The servers, this is the experts, mean doctors. These doctors are 1 to 15 means doctors on call. They are also treated as a regular doctor for the nursing home, because this is the feedback taken from the society, and therefore we have made some assumptions also. Here this data is collected. We have normalized the data. Why we normalize the data? Because the redundancies and the error are absent, and this becomes much cleaner data to apply for the result. And thereafter, okay, this we have implemented this. These are the results. These are the results actually, and you look here the actual ANN by the software. This is our ANN, artificial neural network. You look here. These are weights are computed here. The choice is computed here. Everything is. This is service cost. This is capacity, service cost, waiting line, service. These are the inputs variable, and ultimately we have got the choice. So error is here. Steps is 160. Prediction of the results. It is the prediction of the results, predicted values. The validation is very important. Otherwise, people question that whether this is good or not. The validation is the variance is here. It is comes out. The coefficient of variation is computed. This is also part of the software, and this coefficient of variation is very less. It is expected up to 0.05. And our covariance is much less from this because it has 2.0. So the prediction and classification is valid. Conclusion: we have been able to apply the queuing artificially intelligent queuing model to this. These are the references. I think how many references? Maybe around 51 references. Okay, so I close my this presentation, and thank you very much for giving me time. I am late, 1 minute late, I think.
You are very much in time.
Okay.
Thank you, Professor Mishra. Any query from anybody? So Dr. Mishra discussed the queuing theory in a simple language. He nicely differentiated between queuing, maybe virtual or physical, queuing system, and queuing model and its applications, which is very beneficial to especially to our MSc students and the research students. He has talked about the cost management. We have to keep in mind the cost management while making the queuing system or queuing model. He has talked about the artificial intelligence and machine learning. At this juncture, I would like to suggest the students, those who have interest in computer language, must study one language so that they may apply the queuing model and the artificial intelligence, machine learning. It is a very burning topic, very burning, very vast topic. And he has talked about the healthcare system model, and that is also very challenging and very scope in this field. So the students, research students who are joining today may take the help and the guidance of the department, especially Dr. Mishra, to develop a healthcare system model. He has talked about the basic tools of queuing theory, which is very essential for the students, especially for the students, maybe for other also. And I suggest finally to the students, to research scholars, to please develop mathematical models applying any of the queuing theory, and with the help of any language, any computer language in which they have interest. Maybe the latest knowledge, but in any language that. So Dr. Mishra, thank you for your valuable lecture.
Thank you, sir. Thank you.
Now we have the next session, technical session, which will be chaired by the Dr. Abhishek Singh. Dr. Abhishek Singh is also associate professor of the department, and Dr. Manoj will also chair this, who is also a assistant professor. So I now leave this beautiful munch and over to Dr. Abhishek Singh. Please keep on joining. All the students are requested to join, not to leave. Dr. Abhishek Singh, can you hear me?
Manoj is here, Manoj.
Okay,
Yes,
Dr. Manoj is here. Can you hear me?
Yes, sir.
So
Yes,
please
sir.
share please share this technical session of paper presentation right from now.
Okay, good noon, sir, everyone. Myself, Dr. Manoj Kumar, Assistant Professor in Dr. Rammanohar Avadh University. And in this session, the five presentees are, first one is Santosh Kumar, second one is Sunny Seth, third one is Dr. Sanjeev Singh, and fourth one is Amit Kumar, and fifth one is Dr. Abhishek. So all will be ready. First one, I want to present Dr. Santosh Kumar. Introduce yourself and give your presentation title. Dr. Santosh Kumar, you are present?
Yeah, yes, sir. Am I audible?
Yes, yes.
Okay.
You
Hello.
introduce yourself and give the title of your
Yes.
presentation.
Okay.
Okay.
नहीं बेटा नहीं मीटिंग
Good afternoon to everyone. Myself, Dr. Santosh Kumar, Assistant Professor, Department of Mathematics, Sarda University, Greater Noida. The title of my paper is Computational Methods for Fractional Heat Equation and Harmonic Oscillator. The conformal fractional derivative has been studied by several researchers in the recent past. The main goal of this paper is to study MATLAB simulation of conformal fractional heat equation and harmonic oscillator. A differential equation is an equation relating a function with its derivative as a powerful tool to model real-world problems. It is a frequently used in all sciences and different branches of engineering and technologies. Okay. The calculus dealing with integral derivatives was developed by Newton, Leibniz, and Gauss. Since the invention of integral derivative, the concept of fractional derivative like half derivative was known to L. Hospital as back in 1695. Those fractional derivative and fractional calculus, including fractional differential equation, have the history of more than 300 years. Okay, but this fractional derivative, when applying in the different titles, there are different topics like Riemann-Leibniz fractional derivative. It can be defined as the Caputo fractional derivative. It can be defined as okay. But our study the conformal fractional derivative. Khalil et al. In 2014 to introduce the definition of conformal fractional derivative. It can be defined as T alpha fx equal to limit epsilon tends to 0 fx plus epsilon x to the power 1 minus alpha minus fx upon epsilon. Here alpha is the fractional derivative and lies between 0 to 1. So this conformal fractional derivative can be exist if limit exists, provided the limit exists, and satisfying the condition T alpha f0 equal to limit x tends to 0 T alpha x, and can be defined as T alpha fx equal to x to the power 1 minus alpha f dash x. The function fx is differentiable, okay, so it can be find out the conformal fractional derivative. These are some examples. The function y equal to x square. The classical derivative is dy upon dx equal to 2x, but the half derivative, the conformal fractional derivative lies half derivative d half by upon dx half equal to 2x to the power 3 by 2 using the definition of conformal fractional derivative. Similarly, many more examples, that is y equal to x, the classical derivative is dy upon dx equal to 1. The conformal fractional derivative is d half y upon dx half, या d 1 by 3y upon dx 1 by 3. It can be defined as in lies between 0 to 1. The half derivative is x to the power 1 by 2. These are some properties of conformal fractional derivative. T alpha lambda f plus mu g, this is a linear property. Lambda T alpha f plus mu T alpha g. Similarly, you can find out the product of two functions. It can be defined as the division, okay, t to the power p, the conformal fractional derivatives. T alpha sin bx, the conformal fractional derivative bx to the power 1 minus alpha cos bx. Similarly, T alpha sin bx equal to bx to the power 1 minus alpha cos bx. Cos bx, okay, it can be defined as many more functions of a conformal fractional derivatives. These are some properties. Okay, these are some examples basically. Okay. The conformal fractional heat equation. The general form for one-dimensional heat equation, it is defined as del U upon del T equal to K del 2U upon del X square. This is a classical heat equation. Okay. We want to find out the solution of time fractional heat equation. Del alpha U upon del T to the power alpha equal to K del 2U upon del X square. U is the temperature, T is time, K is diffusivity parameters. X lies between 0 to L and T greater than equal to 0. Now alpha is the fractional derivative, time fractional derivative. So we want to find out the solution of this time fractional heat equation. It can be defined as this here ux comma t equal to summation n running from 1 to infinity sin n pi x upon n e to the power minus n pi upon n whole square k upon alpha t to the power alpha bracket 2 upon l integration 0 to n fx sin n pi x upon n dx. We can find out the solution of time fractional heat equation. After that, we want to the simulation of the classical heat equation and fractional heat equation. This here, the first graph represents the solution of the classical heat equation. The second graph represents the fractional heat equation with alpha equal to 0.3. This is your order, alpha equal to 0.3. Similarly, the third graph represents the time fractional heat equation at alpha equal to 0.5. Fractional order alpha equal to 0.5. Similarly, the fourth graph represents the time fractional heat equation at alpha equal to 0.7. This is a simulation of the classical heat equation and fractional heat equation. Similarly, we can use the definition of conformal fractional derivative in harmonic oscillator. The harmonic oscillator, the classical harmonic oscillator, it can be defined as md upon dt plus k ft equal to 0. But we want to introduce the fractional harmonic oscillator. So we can apply the fractional derivative d alpha upon d to the power alpha plus k bracket close ft equal to 0. Now d alpha f upon dt to the power alpha denotes the fractional derivative. Or we can find out the solution of this harmonic oscillator. It can be written as f equal to c e to the power minus k upon m alpha t to the power alpha. After that, we can find out the simulation of classical harmonic oscillator and fractional harmonic oscillators. So this is a graph of classical harmonic oscillators. Similarly, we can draw the graph with different fractional order alpha equal to 0.3. So this graph represents the fractional harmonic oscillator at alpha equal to 0.3, 0.5 or 0.7. This is a simulation. This is a paper is the curve of numerical methods for fractional analogy of partial differential equations. Herman has presented a beautiful account of applications of classical fractional derivative like Riemann, Caputo, and Leavitt in several engineering areas of physics. But the
अयोध्या में
derivative was introduced.
अब लौटेंगे.
Yes. 2014 or this confirmed fractional derivative many applications, okay, in image processing, signal processing. We can find out the fractional diffusion equations. Recently my first paper is accepted the fractional diffusion equations in image processing. These are some references of fractional derivative, confirmed fractional derivative. Thanks. Am I audible?
Manoj ji,
Yes. Yes,
Now-
yes.
his paper is over. Manoj. Manoj. Okay, any question please on this presentation? Any question? Any query? Okay, there is no query, so a lot of thanks to you. Use a clap for you. Thank you.
Thank you.
Okay. Who is next speaker?
Sir, Sunny Seth.
Sunny Seth, are you present?
Yes, sir.
You are present? Sunny Seth, okay, you are. So introduce yourself, your topic.
Yes,
And
sir.
then please start. You share first, you share. Your time is 10 minutes and 2 minutes for query. 10 plus 2.
Sure, sir. Thanks to you, you have reduced my time a lot because all the basic elements of queuing theory you have already highlighted, Mishra sir. So I had actually to delete some of my slides where I initially discussed about the basic elements of queuing theory. Am I audible perfectly?
Yes.
Okay.
Yes, go ahead.
So my name is Sunny Seth. I am an assistant professor mathematics in Jagan Institute of Management Studies, GIMS, New Delhi. And I am working on queuing models. This is my PhD area and I'm almost at the completion stage. I'm finalizing my PhD thesis. So the present topic which I'm going to share today is the priority queuing model with encouraged arrivals for managing the business effectively. Dr. Bhupender Kumar Som is my guide, PhD guide. So first of all, let us understand the introduction part and the need for this study. I'm skipping all the basic introductory part of queuing models because that is already taken by SS Mishra sir and Rakesh sir in the previous session. So as we all know, the environment today is highly competitive and all the firms are trying to stay ahead of one or the other. So they are trying to come up with various strategies so that they can excel in this competitive environment. So mostly we see that the firms are giving huge deals and discounts to the consumers so that they can attract new customers. So we have basically tried to capture this particular phenomena with a term called encouraged arrivals. When firms give deals and discounts to the consumers gets encouraged to join the system. So that phenomena is encouraged arrivals. And generally, when firms have to encourage more and more customers, they often give some kind of priority to the new customers. Like if you are a first time customer of our company, you will get this special benefit, special discount. If you hold this particular credit card, then you will get additional 2000 rupees discount. So they get some kind of priority while joining that particular firm to do the shopping or any other kind of service in that particular field. So the basic contemporary challenge which we have considered here are the encouraged arrivals and the priority considerations. Because if you might remember around 2 to 3 years back, when Amazon or Flipkart, I think they came up with their big billion day sale. So at that particular time, they could not strategize the kind of arrivals, encouraged arrivals that will come due to that sale period and offers. So their server crashed, I think, within 2 3 minutes once they opened that particular site for the offers. So it is very much necessary for the firms to anticipate in advance and try to use some kind of queuing models in advance to come up with the performance measures so that they can effectively strategize, and they should avoid any chaotic situation when they will actually come up with the deals and discounts. Otherwise, as happened with the Flipkart at that time, their server crashed. So this will be the problem, and such problem will hamper the image and the goodwill of the firm, and it will lead in the ultimate loss of the business. So as I just mentioned, these are two contemporary challenges which I have taken care of in this particular research: encouraged arrivals and priority queues. Now, as any mathematical model needs certain assumptions, queuing model also needs the assumptions which we need to understand and look at. The arrival here occurs one by one in accordance to the Poisson process with the parameters lambda 1, 1 plus eta. Here, eta refers to the encouragement factor, the encouraged arrivals. Those customers who will be of higher priority, they will either have the desired credit card, for which the company is giving more further discounts, or they are getting some discount coupons as a privileged members. They are doing the shopping for the first time. So this eta refers to the encouragement factor of the priority one customers. And if there is suppose 50% increase in the customers due to deals and discounts, the eta value will be 0.5. 125% increase, eta value will be 1.25. And the other normal level customers, normal priority customers, will again arrive as a Poisson process with the parameter lambda 2. And we have assumed here that the service is equally given to both priority and low priority customers. So the service is exponentially distributed with parameter lambda for mu. The discipline is non-preemptive priority procedure. There are two types of priority procedures. One is preemptive and the another one is non-preemptive. In non-preemptive, if a lower priority customer is already getting the service, once his service will complete, only then a high priority customer will join in the head of the line. But in preemptive, what happens, even if a low priority customer is getting the service, his service will be stopped and he will have to come later, and the priority customer immediately joins as soon as he arrives. Generally it happens in the healthcare system. If some very critical patient arrives all of a sudden, so any normal patient who is getting consultation from the doctor sometimes keep him aside, keep him waiting for some more time, and then gives the service to the critical patient. So we have considered non-preemptive priority here, and there is a single server through which the service is provided. And obviously within each of the priority, the services first come first serve basis, and the capacity of the system is infinite. Infinite in the sense that if we take an example of online shopping, so any number of customers, there is no limit, no cap on the limit. Any number of customers can keep on joining and they can do the online shopping and all. So therefore the capacity here is considered to be innately infinite. Now, on the basis of these assumptions of the model and using the Kolmogorov process to list down the differential difference equations, and then finally we can have the steady state equations of the model. So I presented here the steady state equations of the model directly. So I've considered three subscripts here, P, M, and R. M stands for the number of priority 1 customers in the system, N stands for the number of priority 2 customers in the system, and R is that which priority customer is in the service, whether it is the 1 priority customer in the service or the 2nd priority customer in the service. So on the basis of that, these 9 steady state equations can be modeled for this particular scenario. For an instance, if I look at the first one will refer to the 0 customer in the system. So if there are already 0 customers in the system, no priority 1 customer will join. So that is why minus lambda 1, 1 plus eta. No priority 2 customer will join, minus lambda 2. And if there is 1 priority 1 customer in this system, 101, the third one will stand for that first priority customer is taking the service, and he takes the service with the parameter mu and leaves, so that again there will be 0 customers. Similarly, if P02, 012, if there is 1 customer of 2nd priority, he will be getting the service, and once his service will be complete, again the system will be empty. So likewise for 1 customer, 2 customer, N customers, M customers, these are the 9 steady state equation models which are developed here using the Kolmogorov process. Then I have basically tested this for the validity using Laplace transform, and then ultimately solved this using mean value approach. In mean value approach, even if we are not able to have the directly probability values for each and every state, we can still have this using the Little's law and the Pasta law. So using that, these are the results of expected waiting time, average number of high priority customers, low priority customers in the system, in the queue. So these are the results for W1, the expected waiting time of high priority customer in the system. L1, using the Little's law, we can get that. The high priority customers average length in the system. Similarly for in the queue, LQ1, WQ1, and similarly expected time for low priority customers in the system, W2, and average length of low priority customers in the system, L2. So here actually I have combined the Pasta property and the Little's law property to find out all these results using mean value approach for this queuing model. Now once we get all these probabilistic measures, then we can easily get all the measures of performances, other things, and we can try to basically include all these formulas in Excel. We can translate it, and then we can try to have that sensitivity analysis part by varying the arrival rate, how the different lengths of the queues and other things are varying, or by varying the service rate, how various other aspects of the performance measures are varying. So just for an example, I have included one particular diagram of that. Variation in the various performance measures by varying the arrival rate of high priority customers. When high priority customers arrival rate increases, then how various performance measures L1, L2, W1, W2 will vary. So we can see from here in the first graph, the orange part is showing the average number of low priority customers, and the blue line is showing the average number of high priority customers. So when the arrival rate of high priority customer lambda 1 increases by setting other parameters to some fixed value, lambda 2 as 2, mu as 15, and encouragement factor as 2.25. So we can see that first of all, for both these curves, it is showing L1 and L2. So for both these curves, it is increasing, right? So from the above graph, it is evident with increase in arrival rate, the average time spent and average number of both the high priority as well as the low priority customer increases. But we can see here the orange line, the slope is bit high. So what is happening here is obviously the waiting time of the low priority customers and the average length of the low priority customers in the system will be drastically increasing if more and more high priority customers will keep joining the system, because they will get preference. They will be given service first, and low priority customers will have to wait for longer period of time for their service, and they will accumulate and their length will also increase.
Sunny,
Yes,
Sunny
sir.
ji, you have only 2 minutes. And
Yeah, I'm
summarize
done. I'm done, sir. This is the second last slide.
Okay.
So it can easily be seen that as per what is expected out of the variations for the waiting times and for the length of the queue and the length of the system. So the model which we have developed here and tried to formulate it and then simulated all the formulas and got this particular sensitivity analysis part from the data. So it is confirming what actually is expected out of any particular queuing model. Now, finally, the last thing, conclusion. So as in this paper, we have developed a stochastic queuing model with encouraged arrivals and priority consideration. Obviously, this will help the firm to understand its performance well in advance. And once they will get to know that at a particular point of time, how many customers will be there in my system and what will be the waiting time of each and every customer. So they can obviously devise their strategies in a most effective manner so that they will avoid any chaotic situation like what happened 3 years back with Amazon or Flipkart, their server crashed. So they will be able to control those things and they will be able to manage the servers in a proper manner if they need some more servers to be taken care of, and they can include all these things in strategizing their business and for the smooth functioning of their business. We have got all the probabilistic results and solved the model in steady state, and then we got all the performance measures which gives us the clear insight of all the things: average length, average time a customer has to wait in the line in the system and all. So obviously by implementing this system, this particular model, firms can effectively design their strategies and can manage their business smoothly and more efficiently. So that is all from my side. Any doubts, any queries?
Okay. Okay, Sunny ji. Anyone have any query? You can raise your hand or you can send your message in chat box. Okay, no query. So thanks again, Sunny.
Thank you very much, sir.
You
Attending
give
this
nice
mathematical
lecture.
conference is really a privilege for me because I got to know various new trends in mathematics, and especially many queuing theory papers are there. So I got to know more information exactly what is happening around. And thank you, Mishra sir, for correcting certain small words. I also used to say bulking and reneging. So I got to know that it's reneging and barking. Thank you very much, sir.
Okay, thank you. So our next presenter is Dr. Sanjeev Kumar Singh. Introduce yourself, and you have 10 minutes for presentation and 2 minutes for question query. संजीव जी को सर को होस्ट जो है बनाइए सर. हेलो.
Thank you.
Naam Singh sir.
Thank you. Now I'm unmute. Am I audible, Manoj sir?
Yes, you are audible. Do yourself and give your the title for presentation.
Okay. Thank you very much. Myself, Dr. Sanjeev Kumar Singh, Master Assistant Professor in BSc program, Dr. Rammanohar, Avadh University, Ayodhya. Today I am going to present my research article entitled "Analytical Solution of Flow in a Composite Cylindrical Channel Using Brinkman Model." This is a special type model said to be Brinkman model. What is going on? Controls. So there are some outlines like the introduction, formulation of the problem, solution, results, discussion, and a conclusion. And This is here you can see the basic physical representation of the problem. Here is a composite cylindrical channel. It is like analogous region, which it has thickness of A, B, and C. There are some 3 regions: region 1, region 2, and region 3. Region 1 having porous medium, region 3 is also porous medium, and region 2 is clear region. Means permeability means the how much fluid can flow from the region. So here we can suppose the permeability of region 1 is K1, like you can see in the slide. Region 3 of K2, outer region 3 is outer cylindrical channel, region 1 is the inner cylindrical channel, and region 2 is clear region. Like here is no porous medium, it is clear fluid flow. So in this paper we have to use the steady flow of viscous incompressible fluid in a composite cylindrical channel using constant pressure gradient. Here region 1, region 2, and region 3. So we can apply Brinkman equation as a governing equation of the motion of porous cylindrical, and Stokes equation for the clear flow have been used. We have used for porous channels Brinkman equation, and for a clear fluid flow there Stokes equation. Okay, so this is the mathematical formulation. We have used steady flow in the viscous incompressible fluid in a composite cylindrical channel had been considered as we discussed of thickness A, B, and C. So thickness of region 1 is A, region 2 mid clear region is B minus C, and out precision of 3 of thickness C minus B, as shown in figure 1. Okay. So equation 1 is the Brinkman standard Brinkman equation is equation number 1. We have used this to find the solution like rate of volume flow in clear region, porous region, outer cylindrical channel, inner cylindrical channel, whatever we have used. So equation 2, here is equation 2 is the most important thing. Here we have dimensionless variable, because for the solution, for to find the solution in simple form, we have to use the variables in dimensionless. Okay, so equation 2 is the dimensionless variables. Equation 3, here using dimensionless variable, we get the Brinkman equation in dimensionless form. Equation 3 is, so equation 4, 5, and 6 respectively. Equation 4 is the Brinkman equation, for the inner porous cylinder, region number 1. Equation 5 is the equation for outer porous cylindrical of permeability K2, and equation number 6 is the equation for clear region of Stokes equation of the motion. Solution and results. Here in these regions we have no slip condition on the surface of outer cylinder. Means of that here we have suppose there is no slip condition on the surface of outer and inner cylinder. Okay, so continuity of velocity and shear stress on the interface of the fluid. Means of that as the inner region and outer region, at the clear region we have the interface of the fluid which is either maximum or the minimum at r equal to 0, depending on the permeability of the regions, because here the permeability K1 and K2 both are the different. It is maybe constant, it is maybe linear, it is maybe quadratic, whatever we have to choose. Thus, we have the boundary conditions, like there are 6 boundary conditions. You can see in the slide where Q1 and Q2 are the ratios of the thickness of the inner and outer regions or clear regions thickness. So, general solutions of the equation of 4, 5, and 6, which are earlier in region number 1, region number 2, and region number 3. All solutions like small u is the solution for the inner porous cylinder. Capital U is the general solution for the equation number 5, which is the outer porous cylinder, and equation number 9. Equation number 9 is the clear fluid region represented by equation number 9. Here all the constant. Actually, there are A1, A2, B1, B2, C1, and C2 are the constant of integration, which is a very large value. So I have introduced that value here by using boundary conditions. With all equation number 7, 8, and 9, with these we can find the velocity velocity by equation number 10. But here the difference, here is the difference in all the velocity, because a limit you can see alpha tends to 0 and beta tends to 0. Here alpha and beta are the porous parameter, where it will be infinite. If it will be infinite in all the regions, mean in the limiting case we have used alpha and beta tends to 0, means permeability will be infinite in the porous medium. So we can find the velocity by equation number 10 in all the regions. You can see here, this is the very important graph for the velocity on the in all the regions. Here you can see for some alpha and beta, some specific value, you can choose any value. Equation reason number 1, reason number 2, and reason number 3. You can see here is increase in with some specific value of alpha and beta, which is the porous parameter. In this equation, reason number 1, it is increasing. Again, in equation number 2, which is the clear fluid region, you can see it is increasing and stable for some time and decreasing. And equation number 3, which is the permeability of other, like you can say constant, linear, or quadratic, it is continuously decreasing in all the regions. So means of that, this is the variation of velocity with radial distance r for the sum values of alpha and beta, which are the porous parameter in inner porous cylinder and outer porous cylinder. So this is the case. And next is the rate of volume flow, in which this is for total rate of volume flow in our structure. We find all the rate of volume flow like Q1, Q2, and Q3 for inner porous cylinder, for outer porous cylinder, and the clear region. We have add and find the final equation for by equation number 11. Here also the dimension is volume flow rate Q0, represented by Q0 for clear fluid flow can be obtained by equation number 12, where alpha and beta also tends to 0 because permeability will be infinite. Here you can see for some specific value of beta, you can see this is continuously decreasing. So this is again for some specific value of alpha, which is the porous parameter of region 1, which is the inner porous cylinder. It is also decreasing with respect to other porous parameter beta. Average velocity by equation number 13. It is also alpha and beta, where porous medium is infinite. Average velocity in all the regions by equation number 14, which is the average velocity for classical Hagen-Poiseuille flow. And last, shear is just on the impermeable surface of the channel. Equation number 15 and 16, both 15 for the inner porous cylinder and 16 for the outer porous cylinder. And again, this is the shear stress with respect to alpha for the specific value of beta, which is the porous parameter for the region number 2, which is outer porous cylinder, are same as we can find. This is also for some specific value of alpha with respect to porous parameter of region outer porous cylinder. This is the variation of shear stress on the outer cylinder with permeability beta for the different value of alpha. Dashed curve is alpha is equal to 2, and plain curve is alpha equal to 5, where Q1 and Q2 are both are different. Q1 and Q2 both are the ratios of the thickness of the inner and outer porous cylinder. So discussion is okay, which is the decreasing or increasing or stable in all the regions. You can see in the graph also. So this is the conclusion of what actually the force viscous in composition fluid which are taken in the composite porous cylindrical channel has been investigated by Brinkman and Stokes equation. Stokes for the clear region and Brinkman for the inner and outer, which is the annulus region with a porosity. With porosity, you can say for inner is K1. K1 is the K1 here. Here is the what is the special case. K1 which can be constant, it is linear, it will be quadratic, same as for the permeability of K2. So analytical solution have flow with the channel has been obtained. We found the variation of permeability and gap parameter has remarkable effect. We can see in the graph for velocity, rate of volume flow, or the shear stress. So result can be obtained by very useful in application of extraction of oil and filtration in industry. Fluid dynamics is also applicable in mechanical engineering, very well. So this was the paper of composite coastal cylindrical channel with permeability variation. These are the references. It is paper is. So thank you. If you have any question with this, you can.
Anyone have any query? A question? Okay, Dr. Sanjeeva, you have gave nice lecture, and in which you discussed about incompressible fluid, porous cylindrical channels. All these things are applicable in the uh, field of applied mathematics. So nice lecture, and thanks again.
Thank you, sir. Thank you. Thank you. Thank you very much.
Okay. Now the next presenter is Mr. Amit Kumar. You are ready? Mr. Amit Kumar.
Sir, he is not present here.
Okay. So next one is Dr. Abhishek.
Yes, sir. Dr.
So-
Abhishek sir is present.
Okay, sir. Okay, thank you.
Okay, Dr. Abhishek, you introduce yourself and give your presentation of title.
So, sir, screen is visible.
Yes, sir. Yes, sir.
Okay. So, a very good afternoon to all of you. I am Dr. Abhishek, Assistant Professor in Applied Science and Humanities Department with Mathematics stream, IT, Dr. Rammanohar, Lohia, Avadh University, Ayodhya. So, first of all, I would like to thanks to convener and all organizing team member of this international e-conference to present one of my research paper with entitled a new approach of moving average forecasting model based on two factors fuzzy time series. So these are contents of my presentation. First one is introduction, then after some basic definition, computational steps of proposed method, defuzzification process, numerical illustration, conclusion and comparison, and references. So this is introduction part of my presentation. So in literature, various forecasting model have been implemented on university enrollments, temperature prediction, weather forecasting, and stock index forecasting that are based on 40 time series model. So the major objective of many researchers is to provide better forecasting accuracy rate in the field of fuzzy time series. Initially, the fuzzy set theory was proposed by Jade, and it was first applied by Song and Chisholm to handle imprecise data and implemented his forecasting model on university enrollments of Alabama. So after that, different researchers have developed time series forecasting model in fuzzy environment. So the main motivation of this present study is to develop a new approach to handling forecasting problem based on moving average in two factors fuzzy time series data. So to prove the performance of the developed method, we use the historical time series Sensex data of Bombay Stock Exchange, that is BSE, and the proposed method define a new technique to partition the inverse of discourse into number of overlapping interval based on number of observation available in the transformed moving average time series data set. So in this study, actual Sensex data is not used to define inverse of discourse, while transformed moving average data set are used in partition.
Dr. Abhishek,
Okay,
your slide is not visible.
Slide is not visible, sir.
Yes.
It is visible.
Yes, you are sharing the screen. Oh, yes. At time visible. Okay. Okay, you can start. You may start.
Okay, so these are some basic definition of my presentation. So fuzzy set, if X is a collection of objects denoted generically by X, then a fuzzy set A in X is a set of ordered pair that is defined as in equation number first. Then fuzzy set A is X mu AX, where mu AX is membership function or rate of membership of X in A that map X to membership space M. So all the membership value of any object can lie between this 0 and 1. So these are triangular membership function. So if a fuzzy set A on real line R with membership function this mu AX from R to close interval 0, 1 is called a fuzzy number, and this fuzzy number A defined by triplet ABC is said to be triangular fuzzy number if its membership function is defined as in figure 1. So this figure 1, we can see that a point B is a peak point where the membership function can define be 1, and when the point is between A and B, its membership value is defined as X minus A and this B minus A, and if X is lies between B and find C minus X upon C minus B, and 0 if otherwise. So fuzzy time series, after that we define fuzzy time series. Assume that this yt t denoted as time, a subset of real number with the universe of discourse on which this fuzzy set fit are defined. Fit is fuzzy set, t is different time at which different fuzzy set are defined. So if this capital Ft is a collection of this fit, so then Ft is called fuzzy time series on yt. So this is fuzzy. Similarly, we define fuzzy relationship. So here Ft is a fuzzy set at time t, and Ft minus 1 is a fuzzy set at time t minus 1. So there is a relationship between Ft and Ft minus 1. So this can be denoted as like this: Ft minus 1 tails to this Ft, and there is a fuzzy relationship between Ft and Ft minus 1, which is expressed as this equation number 2, where this Rt minus 1 comma t is referred as first order model of Ft. If this t is independent of time t, then this is said to be invariant fuzzy time series, and if it is dependent, then it is called time variant fuzzy time series model. So in this study, we use two factors of fuzzy time series data. So two factors fuzzy logic. First, we define two factors fuzzy logical relationship. So here assume this FTBA fuzzy time series. So why we call two factor? Because at the same time we get two fuzzy sets. Means this F1 t minus 1, F2 t minus 1 means that t minus 1 at the same time we get two fuzzy set F1 F2. This can be derived by this Ft. So this notation is called two factors first order fuzzy time series model. So here new concept in this study that is also used, that is moving average model. So what is moving average? A moving average is a computation to analyze data points by making a series of average of different subset of the total data sets, presented a series of number and a fixed subset size. The first component of the moving average is obtained by getting hold of the norm of the initial fixed subset of the number series. So here a moving average can be defined: 2 yearly moving average, 3 yearly moving average, 4 yearly moving average, and so on. So for example, any actual data set we can take. This actual data set be A, B, C, D, E, F. So from this data set we can define 2 yearly moving average. So this actual data set can be converted into this A plus B, A plus B by 2, B plus C by 2. So these are all converted into moving average data set. So a moving average of period n can be mathematically expressed as by question number 3. So where MT is a moving average for the coming period at point t. t, and n is the number of period, where all these xt minus 1, xt minus 2 are actual data set. So these are computational step of my proposed model. So first, collect the historical time series data and further calculate 2-period moving average data set using moving average approach from actual observation of data set. So we have a collection of 2-period moving average historical data set observed from actual observation of data set. So in step 2, we can define this U. U is universe of discourse, is defined as D minimum minus D1, comma D maximum plus D2. So what is D minimum? D minimum is a minimum observation from that actual observation. And what is D maximum? D maximum is maximum observation of that observation. And D1, D2 are two constant that we can easily define the partition of inverse of discourse. So in step 3, we construct
okay,
triangular.
Dr. Abhishek, you have only 2 minutes to summarize your work.
Okay, sir. In step 3, we can define this triangular fuzzy set, and after this, we can define variation data set in step 5, and similar process we can done in step 6 for variation data set. We define inverse of discourse for this, and after that triangular fuzzy set are defined from this variation data set, and these are similarly, these are defuzzification process. How defuzzification process is very important. It means it can conclude that our proposed method is give better forecasting accuracy rate over the existing fuzzy time series model. So here these RMSE and AFP. These are root mean square error and average forecasting error. These are common tools to measuring the forecasting accuracy rate, which are defined. So these are data set. First column is from we can take data from 1st January 2012 to 29 February 2012. There are 42 number of observation. These are open observation, and these open observation can be converted by the help of moving average concept. So third column is moving average data set. We can after that we can fuzzify this fuzzified moving average data set, and this variation data set is come from this data set, moving average data set, and this variation data set again fuzzified by the another fuzzy number BI. So after that, these are triangular fuzzy set for the main factors data set, and these are calculated membership rates of this triangular by the help of this triangular fuzzy number, and this variation data set similarly we can calculate. These are fuzzy logical relationship group by define the calculated data. So these table we can these are open observation, and these are proposed method by which we can obtain the forecasted value. These are chain method. We can comprised by 3 authors: chain method and Huang U model and Hurong and Q type 2 model. So at the end, by the graph, we can show that this proposed model based on 2 factors fuzzy logical relationship are significantly closed in according with the open observation. This red line shows the proposed method, and this violet line shows the open observation of data set. So this is conclusion, and in comparison we can see that our RMSE and AFE average forecasting error is very less, 1.04 comparison to these 3 authors. So we can conclude that our proposed method can give better forecasting accuracy rate. So these are references used, and thank you. So if you have any question, then you can ask.
Okay, okay, Dr. Abhishek. Anyone have any query or any suggestions? Okay. So Dr. Abhishek discussed on fuzzy sets and used some membership functions, and he gave a nice presentation. And thanks again.
Thank you, sir.
This ends the session of paper presentation. Okay, thanks again, everyone. And
उसके बाद
time
कुछ
for
है क्या?
no, sir.
What?
Time for lunch from 1 to 2:30, and next paper presentation from 2:30 to 3.
कौन कौन है उसमें?
उसमें सर 3 लोग हैं.
कौन?
संदीप रावत जी हैं, बीबी सिंह हैं, और एक और है सर.
संदीप रावत और
सर वीर बहादुर सिंह,
हाँ,
और एक लोग और हैं सर.
कौन है एक लोग को?
एक मिनट सर, बता रहे हैं सर.
Sir, one is missing Amit Kumar.
अमित कुमार सर इस टाइम पे थे, वो अभी नहीं है.
नहीं, इसमें नहीं, उसमें कितने लोग हैं जो आपका
हाँ सर बता रहे हैं.
आधे घंटे का, उसमें 3 लोग हैं, 2 लोग हैं?
Sir, Sandeep
सर
Rawat
उसमें
ji and BB Singh ji.
हाँ हाँ, बीबी सिंह,
संदीप रावत और बीबी सिंह हैं.
हाँ.
सर संजीव कुमार जी दे चुके हैं, तो अगर अमित कुमार जी उस समय प्रेजेंट नहीं थे, अगर इसमें देना चाहेंगे तो 3 लोग रहेंगे, नहीं 2 लोग हैं सर.
अब अमित कुमार का जब था उन्होंने नहीं दिया ना, खत्म हो गया.
यस सर, यस सर.
कोई नहीं, क्योंकि हमारा वैलिडिक्टी शुरू हो जाएगा ना.
हाँ वैलिडिटी सर 3 बजे से. यस.
हाँ, उसमें कहीं कुछ ना करो, हमारे पास भी आया था, हम किसी के अलाउ नहीं किए हैं
ठीक सर, तो
presentation के लिए.
2:30 से 3 में जो है सिर्फ 2 लोगों का होगा सर.
अब ये सब जो है इनडिसिप्लिन लोगों के लिए नहीं होता है कि
यस सर.
पेपर नहीं भेजे हैं, टाइम से नहीं आते हैं, कर नहीं पाते हैं. इतनी सिंपैथी नहीं रखना चाहिए, नहीं डेवलपमेंट नहीं होता है. अच्छा, तो ये संदीप बचे, बीबी सिंह, तो हमें लगता है संदीप तो देंगे, बीबी सिंह का भी निश्चित नहीं होगा. चलिए ठीक है फिर.
सर
ठीक है.
ओके, थैंक यू सर.
Okay. So session is over. We will meet again 2:30.
Yes sir, 2:30.
2:30 we will meet again. All the students are advised to be connected very positively. And Sangharsh ji is advised to make the contacts with Mr. Rajiv Kumar so that we can start it 5 minutes earlier. Okay. So
Okay, sir.
thank you very much to all.